Hi, my name is Abdulrahman. This is our group presentation. So I'm going to present part A, which is about the review of the research papers. There were four research papers related to computer architecture and organization. So we were focusing on summary, where each paper was analyzed for its strength, limitation, and potential improvements. So there were four papers. So here one of the uh, topics that these papers were covering. So paper one, which is analog in memory computing, LIMCA, which is covering about the using LLMs to automate analog hardware architecture design. For paper two, which is the titled supply chain aware architecture, covers embedding supply chain considerations in architecture design. For paper three, which is related to chip design and semiconductor uncertainty, supply and demand, where it covers applying design flexibility to reduce risk from supply-demand fluctuations. Paper 4, Programmable Accelerators for Data Access, DX100, where it covers accelerating irregular memory access using specialized coprocessors. And here we're going to see the key takeaways from each paper. For paper 1, LLMs can accelerate analog architecture design. That's the paper, the title of the paper. So one of the key takeaways from this paper is like LMAC shows how AI can streamline manual and time-consuming design processes. For paper two, architecture effective supply chain resilience and embedding supply chain models in architecture helps avoid disruption and delays. One of the key takeaways from paper three is designs with adaptive and distributed strategies reduce exposure to market instability. And from paper four, the one of the key takeaways is offloading indirect memory operation boosts system efficiency and lowers energy. Lastly, this paper shows how modern computer architecture is evolving to meet real-world challenges like supply chain stability and performance bottlenecks in memory access. For example, in paper 1, LMIC showed how AI tools can help automate architecture design. The supply chain paper highlighted how architecture decisions can reduce real-world risk, and the X100, which is paper 4, showed that offloading direct memory access to specialized hardware greatly improves system efficiency. That's all. Thank you.
Hi, I'm Eileen. Today, I would like to introduce a useful tool called SMP Cache. SMP Cache is a simulator that helps us learn about cache memory systems, especially in symmetry multiprocessors, or SMP for short. It was created to support education and research. The simulator is easy to use and runs on Windows. It has a visual interface, so we can actually see what's happening, which makes it easier to understand complex ideas. With SMP Cache, we can test how the number of processors affects system performance. We can also try out different cache mapping methods and study cache coherence protocols, all by using simulation. Overall, it's a great way to learn through hands-on experience. Whether you are a student or researcher, this tool makes understanding multiprocessor caching much simpler. For this part of the project, I tested 9 different trace files using seed associative mapping. The programs I used were Hydro, NASA7, CEXP, MDLJD, EAR, COMP, WAVE, SWM, and UCOMP. I changed the cache size step by step. The smallest size was 0.03 kilobyte, and the largest was 16 kilobyte. For each size, I recorded the number of local hits and local miss from the SMP cache simulator. The goal was to see how cache size changed the miss rate. In most cases, I saw the larger cache give fewer miss, but different programs show different patterns. Some needed a small cache to improve, and some needed a much larger one. This helped me understand how memory access works in different programs and how important cache size is for performance. Now, I will share the data I found. I list out 4 programs, Hydro, NASA7, COM, and WAVE, and measure their hit and miss rate at different cache size, from really small one like 0.03 kilobytes up to 16 kilobytes. As the cache gets bigger, we see that the hit rates get better. For example, with only one cache block, which is about 0.03 kilobytes, the hit rate is pretty low, around 33 or 34%. That means most memory accesses result in a miss. But when we increase the cache to 32 blocks or 1 kilobytes, the hit rates jump up a lot, reaching around 78 to 83%. That's big improvement. This improvement keeps going as the cache grows, but only up to a point. Once we reach around 8 kilobytes or 256 blocks, the hit rate doesn't change much anymore. So adding more cache after that doesn't really help as much. We call this diminishing returns. One interesting thing, we noticed that the COM program always had better hit rates the others, especially when the cache was more. On the other hand, web had lower hit rates in general. This likely means the program access memory in different ways. Some may have better data locality than others. To sum it up, bigger cache usually help reduce miss rates, but only up to a certain size. After that, the benefits slow down. Knowing how different programs behave help us smarter choice when designing system and deciding how much cache we really need. In this project, I tested how cache size affect the miss rate. When the cache gets bigger, the miss rate goes down. That's because the cache can store more data, so the system doesn't need to go to memory as often. We use fully associative mapping. That means any data block can go into any cache line, so there are no conflict miss. All the programs I tested show better performance with bigger cache, but they have behaved differently. For example, CEXP.prg had a big drop in miss rate from 52.9% to 0.7% when the cache size went from 0.03 kilobytes to 1 kilobytes. On the other hand, MDLJD.prg needed a much bigger cache to improve. This shows different programs had different memory needs. When the cache size got large enough, the miss rate stopped changing much. This is because the cache could already hold the important data. At the point, only compulsory miss were left, which happened when data is accessed for the first time. Some programs had a sharp drop in miss rate at a certain cache size. For example, CEXP.prg improved a lot at just 0.5 kilobytes. Other programs had their own special points. This tells us that every program needs a different cache size to work best. In short, increasing cache size helps performance, especially for programs that use memory a lot. That's all from me. Thank you.
Hi, I'm TAO6123. Now I will talk about the version control system with GitHub. GitHub is a web-based platform for version control and collaboration. It is built on Git. GitHub stores code in repositories. It values you in open source and professional projects. User can use the GitHub for track, change, and project history. After that, user can use pull requests for code reviews and merging. User also can use GitHub Action for workflow automation. It supports both public and private repositories.
Demo about the GitHub. First, we go to File. We create a new repository. We name it as description. Then we create it. Remember to tick this. Then we create the repository. Then we publish. Okay, after we publish, we click this show in Explorer. We add a new txt file, name it as member, and enter. Then we back to GitHub, and at here we write created member dot txt. Then commit it. Okay, then push origin. Then we go to view on GitHub. You can see here, we just commit. Here the member, just commit now. Then we go to setting. We want to add collaborators. Then we click here, add people. Okay, after we key in the collaborators email, that's all from me. Next, I'll pass to Huichi as a collaborators.
Hi, I'm TAO6123 and now I will continue to the next step. First is click the accept invitation. After that, we need to copy the URL of the repository that need to clone. After that, we paste the URL and click clone. After that, we need to open the member.txt file and insert my full name. Then save the document. After that, exit the member.txt file and back to the desktop GitHub. And insert add my name to member.txt. Then click push origin and view on GitHub. Now we can see the updated.
And now I will talk about the Git version control system. Git is one of the most popular version control system VCS to managing multiple versions of code, collaborating seamlessly across team and keeping to track of change. Git helps to manage code base efficiently, version are maintained, and collaborating is smooth. It developed by Linux Robot. Git has established itself as a leading tool for source coding management in software development since 2005. And here is the difference between Git and GitHub. For the nature, Git is a software tool and GitHub is a service that provides a platform for hosting Git repositories. For the interface, Git is a common line tool and GitHub offers a graphics user interface. Third, for the maintenance, Git is a maintenance by the Linux community, but GitHub is maintenance by the Microsoft. Lastly, for the user management, Git does not have built-in user management feature, but for the GitHub include user management and access control.
Hi, I'm Linkinson. Next, I will talk about key features and benefits of using Git. Git simplifies team collaboration by allowing multiple developers to work on the same project without conflict. Each developer has a full local copy of the repository, improving speed and reliability. Besides, branching in Git is fast, lightweight, and support organized workflows. Feature branches ensure changes are tested before merging into the main codebase. Git tools like pull requests and merge capabilities support smooth code integration and peer review. Next, I will talk about conclusion. Git helps manage and track all changes in all project source code efficiency, allows recovery from mistake by reverting to previous versions, centralize the project structure, keeping all source code both low level and high level in one place, maintains a clear history of changes, making it easier to understand and review updates. It also enables team members to work independently without interfering with the main code base. It also supports mixed language projects, handling various file types and edits smoothly. It can improve collaboration, clarity, and code quality across the development team.